Okay, so let's get started on day 3 of the April 2021 meeting of the Mid-Atlantic Fishery Management Council. We are going to start off this morning with a presentation from Dr. Vincent Seba with the Northeast Fisheries Science Center on climate change science efforts underway at the center. So welcome, Vincent, and the floor is yours.
Thank you so much. And just quick audio check. Can you hear me okay?
Very loud and clear.
Excellent. Thank you so much. Good morning, everybody. And thanks for having me. I appreciate the opportunity to present some of the latest fisheries climate research that we've been doing at the Northeast Fisheries Science Center, as well as some new things that are in the works that I'd like to talk about as well. I'll try to keep my talk to about 30 to 35 minutes so we have room for some time for discussion and questions. But again, my name is Vince Saba. I work for the Northeast Fisheries Science Center's Ecosystem Dynamics and Assessment Branch. But I sit at NOAA's Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey, which is NOAA's primary climate modeling lab. So I'm able to work with climate scientists at GFDL and modelers to use their models and research and apply those to fisheries climate research questions in the Northeast US. So the outline for my presentation today will essentially cover 5 themes. The first part, I'll talk about the observed changes in the U.S. Northeast Shelf. Some of these things you probably saw yesterday in Sarah's State of the Ecosystem report, so I'll just cover a few of those. And then I'll talk about the National Climate Science Strategy, which is now 6 years old, and also our Northeast Regional Action Plan, and some updates to that. And then I'll talk about our Regional Action Plan accomplishments over the last 5 years. We just put together a 5-year synthesis report of our accomplishments in the Northeast. And I'll mostly focus on our vulnerability assessments, scenario planning, laboratory studies, some of the new work we've done in our climate enhanced stock assessments, and population dynamics models, and species distribution projections. And then I'll finish off with what's needed to achieve climate-ready fisheries management, and where I think we need to go in terms of improving our ability to communicate with stakeholders and provide them the best available climate fisheries science. And then finally finish off with the new NOAA Climate and Fisheries Initiative, which just wrapped up last year in terms of the first draft. So just a brief primer on the U.S. Northeast Shelf oceanography. I know a lot of you have seen this figure before. I'll give you some context into some of the figures and ocean model simulations that I'll be showing today. So the U.S. Northeast Shelf is a relatively complex coastal system that sits at the interface of 2 major current systems, the Gulf Stream coming from the south, which is the warmer, saltier current, and the Labrador current coming from the north, which is the colder, fresher current. And essentially, these currents can enter the Northeast Shelf in 2 different ways. One way, in terms of the Gulf Stream, are through these warm core rings that are anticyclonic mesoscale eddies, which can last from weeks to up to a month, and are depths about 1,500 meters or so. And these can enter the shelf, and they're known to cause marine heat waves when they can persist in shelf waters. Another way which these currents can enter the shelf is through the Northeast Channel in the Gulf of Maine. And so our NOAA surveys go out every year, measure temperature and salinity from the ocean, particularly the Northeast Channel, where we can get a sense of the proportions of these currents entering the Northeast Shelf. And so I'll show some figures in just a bit what those 2 currents have been doing over the last 10 years or so. But it's a relatively complex system, and it's a very difficult system to model in terms of ocean simulations. So what do the trends look like in terms of temperature warming? So Sarah touched on this a bit yesterday. I'll just go into a little bit more detail in terms of the physics. So essentially, looking at the Mid-Atlantic Bight, which is highlighted here in the gray region, each panel here shows the sea surface temperature anomaly for the year 2020. And this is using satellite-based measurements of sea surface temperature. This is daily SST, and this is the anomaly based on the 1982 to 2011 climatology. So red areas are where the ocean was warmer in 2020, and blue areas are where the ocean was cooler than average in 2020. And this is based on daily data, and this is broken down through winter, spring, summer, and fall. So what you can see is that in terms of the ocean warming in the mid-Atlantic, the spring had some cooling in the mid-Atlantic bight and some regions that didn't warm at all. However, if you look at the fall and summer, we saw somewhat substantial warming in the fall, closer to average conditions in the summer, and winter was also closer to average. But if you look at the long-term trends in the Mid-Atlantic bight in terms of SST, what you can see is that the spring, summer, and fall have all warmed substantially since 1982, with the summer having the largest warming rate at half a degree per decade, the spring being the lowest warming rate, and fall somewhere in the middle. However, what seems to be consistent between the New England waters in Georges Bank and Gulf of Maine and the Mid-Atlantic is that the winter temperatures have been relatively stable since 1982. So the majority of warming has occurred in the spring, summer, and fall, whereas most of that warming has occurred in the summer and fall. So we're also starting to look at ocean warming in terms of marine heat waves. So a marine heat wave can be defined as a warming event in the ocean measured by surface temperature measurements, like I showed in that last slide. But the event has to last for at least 5 days or more. And the event is also characterized by the warming within the top 10% of warming in the last 30 years, so the upper 90th percentile. And what you can see for the Mid-Atlantic bight, this is specific. All the figures I'm showing today are specific to the Mid-Atlantic. The number of marine heat waves in terms of cumulative intensity and maximum intensity have all been increasing. So the figure on the left essentially is showing heat waves measured in degrees centigrade days. So you basically summarize all the marine heat waves for the year, look at their intensity and how long they last, and you come up with an index. On the right panel, it's essentially looking at the warmest heat waves for that year. And these are calculated up through 2020. So in 2020 for the Mid-Atlantic bight, in terms of cumulative intensity, they were well above average. So we had a lot of small heat waves in 2020. But if you look to the right panel, in terms of maximum intensity, they weren't as warm as they had been in the past. So in 2012, throughout the US Northeast, which is the warmest year on record in terms of our ocean measurements of temperature data, heat waves in the Mid-Atlantic were at their peak in terms of cumulative intensity and also maximum intensity. So we haven't seen a year like that since 2012. But 2020, we did have a lot of smaller heat waves, which are also pretty relevant for living marine resources, even though they weren't as warm as previous years. We've also looked at the Gulf Stream. So this figure here is also from our 2021 SOE. And this measurement of the Gulf Stream is using sea surface height. So we've also used previous measurements of the Gulf Stream index that use temperature-based measurements at 200 meters. This particular index we're using now more often because we're able to get the data more frequently. And so this goes up through 2019. And so what we found with the Gulf Stream is that since about 2010, we've seen a dramatic shift to the north in the Gulf Stream index, with 2019 being the furthest northern, the most northern position on record since this time series started in 1993. So keep that in mind for some of the slides I'm going to show in just a bit. In terms of ocean acidification, we do not have a lot of measurements of ocean pH. Most of these measurements are exclusive to the surface. We're just starting to get at some of the mid-water and bottom measurements using gliders, ocean gliders that have pH sensors on board. But in terms of surface pH, the decline in ocean pH that we've seen over the last 3 to 4 decades has been relatively consistent with global measurements, such that the decline in pH of about 0.08 to 0.1 is relatively consistent with what we've seen in terms of the amount of anthropogenic carbon dioxide entering the atmosphere and then dissolving into the ocean. So the water seems to be becoming more acidic throughout the Mid-Atlantic and in New England waters. So in terms of regional ocean circulation change, if you remember back to that oceanography figure I showed you with the two current systems, the Labrador Current and the Gulf Stream, the measurements that we're taking in the Northeast Channel, where these currents enter at depth in the Gulf of Maine at about 150 to 200 meters, have been changing since about 2010, just like we've seen with the Gulf Stream. So the red time series on top here represents slope water associated with the Gulf Stream, the warmer, saltier slope water. And the blue time series represents the slope water associated with the Labrador Current, which is the colder, fresher slope water that enters the Gulf of Maine. And since about 2010, just like with the Gulf Stream, we've seen a larger proportion of slope water associated with the Gulf Stream entering the Gulf of Maine through the Northeast Channel. So there seems to be a correlation between a more northern Gulf Stream and more of that Gulf Stream slope water entering the Gulf of Maine, which does make sense. So in terms of fish distribution chains, as we've been observing all this warming, we're also closely monitoring our survey data. So this figure here is from the Rutgers University Ocean Adapt website, which is a collaboration of NOAA Fisheries and Rutgers University. And this is showing the center of biomass change throughout all marine taxa in our Northeast Fisheries Science Center bottom trawl in the fall. And what you can see is that if you look at the U.S. Northeast Shelf as a whole, including Georges Bank and Gulf of Maine waters and the Mid-Atlantic Bight, there's been a general northern shift in the center of biomass throughout all the marine taxa that are sampled. However, what is driving this northern shift is primarily coming from the Mid-Atlantic Bight. Kristen Kleisner published a paper back in 2016, which basically broke down the U.S. Northeast Shelf, showing that most of the marine taxa in the Mid-Atlantic Bight are moving to the north, whereas if you look at the Gulf of Maine and Georges Bank, there's more of a southwestern shift, and species are actually going deeper in the north. So most of this trend is being driven by the Mid-Atlantic. Similarly, we can look at changes in depth among all these marine taxa. And again, this is focused on the fall survey. What you can see from this figure is that species are starting to be caught deeper in the water column. And this particular trend is being driven by Gulf of Maine, where we're seeing species moving into deeper water, primarily colder water species seeking colder refuge as the ocean is warming. So that covers kind of a general sense of what we've been observing in terms of some of the major changes in the physics and our survey data. But I also want to touch on what NOAA Fisheries and the Northeast Fisheries Science Center has been doing in terms of addressing climate fisheries and protected species research, and what our plan is for it moving forward. So in 2015, the NOAA Fisheries Climate Science Strategy was published. This was a national guidance document. It wasn't based on any legislation. It was essentially a guidance document for the science centers and regional offices. And the strategy is essentially part of a proactive approach to increase the production, delivery, and use of climate-related information to fulfill NOAA fisheries mandates in a changing climate. And this was a quote from our former fisheries assistant administrator back in 2015. So within this national strategy document, there were 7 main objectives that were identified, which were all interdependent. So moving from the top to the bottom of the pyramid here, the first 3 objectives are essentially informing management. So climate-informed reference points, more robust management strategies related to climate fisheries, protected species issues, and then adaptive management processes. So management strategy evaluations that assess climate information, climate risk, and vulnerability. And then objectives 4 and 5 are essentially predicting and tracking projecting future change and understanding mechanisms of change. And then the bottom 2 objectives are essentially tracking change, looking at our observations, forecasting, providing early warnings, and also building and maintaining an adequate science infrastructure so that we can continue to address these climate change issues. So the national document required each region throughout the National Marine Fisheries Service to produce a regional action plan. So in the Northeast, this is called our NERAP, the Northeast Regional Action Plan. And this was published back in 2016. So the document is now just about 5 years old. And we're actually currently under development of a NERAP 2.0. And we're trying to have our draft reports, our draft documents done by this summer. So the document's now 5 years old, but essentially what the document did was it looked at all of our current research and basically took the 7 objectives from the national document that I just showed you in the previous slide and organized them into 15 priorities throughout the 5-year period from 2016 to 2021. And we looked at those priorities in terms of existing funding lines versus new funding lines. So no new resources versus new resources, and the kind of things we'd like to get done in that 5-year period. And so we just finished our synthesis report looking at the last 5 years, which I'll cover some of those highlights today. So one of the major things that was accomplished since the NERAP was published was the climate vulnerability assessment that was published by John Heyerdahl and PLOS One in 2016. And this particular figure here is relevant to the mid-Atlantic species. There were over 80 species that were assessed in terms of their vulnerability to climate change, looking at things like ocean temperature change, ocean warming, ocean acidification change, predator-prey changes, things like that, species distribution changes. And what they found in this vulnerability assessment were that some species were suggested to have a positive effect with, respond positively to continued ocean change. Some species had a neutral or no vulnerability, versus some species having a negative vulnerability. And those were Atlantic mackerel, surf clam, ocean quahog, alewife, and American shad, whereas black sea bass, bluefish, butterfish, longfin inshore squid, northern shortfin squid, and scup were suggested to have a positive response to continued ocean change. So this was a vulnerability assessment. There weren't any long-term climate change projections or distribution analyses in this study. It was a vulnerability assessment. So now we've taken this paper and we've applied this vulnerability assessment to other assessments. So for example, there's a sea turtle and marine mammal climate vulnerability assessment, which is currently underway. The marine mammal assessment was done nationally, and that's currently published. The sea turtle vulnerability assessment is currently in review and will hopefully be published this year. Folks in the Northeast have also made tremendous progress on the Northeast Habitat Climate Vulnerability Assessment, and that is in its final phase. We've also done some substantial work within our social sciences branch. So this is a paper by Lisa Colburn et al. Published in 2016, and they looked at all the ports throughout the US Northeast in terms of their vulnerability to future climate change. And what they found were that the ports that had a higher diversity of catch had a moderate, low to mixed vulnerability, whereas those ports that had a less diverse catch had a higher vulnerability. So ports that were mostly catching just sea scallops, that were mostly landing lobster, had a higher vulnerability, and they were basically projected to have less adaptation to future change as the ocean is continuing to change. We've also made some substantial progress on scenario planning. I know the Mid-Atlantic Council is in the process of the US East Coast Climate Scenario Planning Project. And this is something similar that we've done and just published for right whales, North Atlantic right whales, and Atlantic salmon. So these are two protected species that have received a lot of attention. And this effort was mostly led by our regional office, GARFO. And both of these documents were both recently published in the last 2 years. But the idea behind the scenario planning was to basically help manage risk and prioritize management actions in the future. So looking at different long-term scenarios for right whales in terms of climate change and Atlantic salmon, and looking at different potential outcomes, and essentially exploring what NIMS can do to improve species resilience in the face of continued climate change. We're also very, very much reliant on our laboratory studies. So at our labs in Sandy Hook and Milford, we're conducting process-based laboratory studies both on finfish, also on phytoplankton and shellfish. And these studies can range from looking at changing water pH and their impacts on, for example, larval summer flounder, to studies looking at ocean acidification or warming on shellfish. And these studies are critical to inform our models when we're looking at historical hindcasts or projections or even near-term forecasts. We need to include variables beyond ocean temperature. So we rely on these laboratory studies, these process-based studies, to inform those models. We've also made some progress on incorporating climate into population models. Now, these aren't looking at, for example, climate information into operational stock assessments, but at least looking at some key species in the Mid-Atlantic. In this case, we've mostly looked at black sea bass and summer flounder, and seeing how if in the incorporation of environmental variables can enhance our historical hindcast of species population dynamics, or even reducing stock assessment retrospective patterns. And so some of these species, for example, like summer flounder and black sea bass, have known linkages to environmental covariates, and using these species was basically an easier thing to do because we already had existing information on their links to the ocean environment. And so some progress was made there. But what we're trying to do is get these into more of an operational sense, which of course is can be quite challenging. We've also done a lot of work, particularly the work that I've been doing, looking at global climate models. So the work that we've been doing in collaboration with NOAA, GFDL, and Princeton has really focused on looking at higher resolution ocean models. Global climate models were not really designed to assess coastal climate change. They're really looking at basin scale, ocean scale, global scale change. But of course, as you all know, fisheries are occurring in small regions along coastlines. And so it's really critical that we have these higher resolution ocean models when we're assessing and predicting future climate change impacts on our living marine resources. And so this just gives you a sense, if you look at the animation on the left, the higher resolution ocean models that we've been using in the Northeast Fisheries Science Center when we're projecting long-term future change for the marine taxa that we're interested in. The right-hand panel, which are these typical coarser models, really don't give you a good sense of the regional circulation. They don't resolve the regional circulation of the shelf. The Gulf Stream isn't where it should be. And we really need to have these regional circulation features resolved when we're talking about future ocean change. So in terms of the projections from these higher resolution versus coarser resolution models, I know some of you have seen this figure before, but just the key take-home message here, what this is showing are projected changes in ocean bottom temperature under a doubling of atmospheric CO2. And so the models that are in the upper left panel, the top right and lower left are lower resolution models, and the bottom right model is the highest resolution model that GFDL, it's a prototype model called CM2.6, but it's the model that we've been using, which is about a 10-kilometer nominal ocean resolution in the horizontal. So this is basically like your 4K television model versus these models here are your 1080p and standard definition television models. And so what you can see is that when you increase atmospheric CO2 in these high-res models, we essentially get non-uniform warming throughout the US Northeast Shelf, particularly in the Gulf of Maine and along the shelf break, where you can see bottom temperature, there's an enhanced warming in the bottom temperature. And what's causing that is the Gulf Stream is moved further north, pushed further north as CO2 increases in the atmosphere, and more of that Gulf Stream slope water is entering the Northeast Channel of the Gulf of Maine. And this is exactly what we're seeing in our in situ measurements over the last 10 years in the Northeast Channel. So the model seems to have agreement with our observations in terms of the high-res model projection versus the coarse models. We don't see this, and we don't see this uniform warming in our SOE reporting as well. That figure I showed you earlier, you can see that there was a seasonal difference in the warming, and we're also still seeing a more substantial warming in the Gulf of Maine relative to the Mid-Atlantic bight. So the Gulf of Maine has in fact been warming faster than the Mid-Atlantic bight over the last 20 years. There's also been some recent work to essentially, essentially to build off of the work that we did back in 2016, looking at the global high-res model. Mike Alexander and colleagues have taken the ROMS regional model and they've coupled it into 3 different global climate models and simulated ocean change using the RCP 8.5 high emission scenario, which was the AR5 assessment from the IPCC. And so this paper was published 2 years ago. And essentially what they showed was that the regional warming in the ROMS model, when coupled to 3 different climate models, is essentially a function of how much the global climate model warms. And so the 3 global climate models they chose had different warming rates. But I think the interesting thing in this analysis compared to the analysis in 2016 is that the warming along the US Eastern Seaboard is relatively uniform in the 3 different ROM simulations. But the global high-res model shown on the left still shows that non-uniform warming that our observations are showing. So I think what we need here is more of these ensemble high-resolution simulations to really get a sense of model uncertainty. 3, 4, 5 models is just not cutting it. It's just not enough. We've also made some substantial progress on our projections of species distribution. So this was a paper that we published back in 2019, where we looked at pretty much all of the marine taxa in our survey, in our bottom trawl survey, but we also included fisheries dependent data as well. So we didn't just look at our fall and spring survey data, we included 12 months of the year for each year for all the species using all of the observer data that we have that was somewhat comparable to our bottom trawl survey, so mostly coming from bottom trawls. And then we also incorporated variables beyond temperature. We looked at things like bottom salinity, surface salinity, bottom temperature, surface temperature. We also looked at rugosity and sea surface height and depth. And when we combined all these different ocean variables together, even though we didn't know the mechanistic links, say, for example, between bottom salinity and black sea bass habitat, we did find that when we projected forward using the high resolution global model, that the projected thermal habitat or projected habitat of black sea bass, in this case shown here, was different when you use the full model, which uses all the ocean variables, versus the partial model, which only used ocean temperature. So you can see that the future outlook for black sea bass is very different when you incorporate all the model variables, ocean variables, versus just temperature. So this is important moving forward when we're assessing long-term change in species distributions. We know that temperature is important, but it's not the only factor. So when we did the synthesis of our NEREP report, we also looked at the majority of our first authored and co-authored publications coming from GARFO, the Northeast Fisheries Science Center, and Chesapeake Bay office. And when we kind of looked at this, what we found was that the majority of our climate fisheries protected species work has really been based on our observed change, so looking at changes in our ocean conditions, in our surveys, and of course projecting that future change long term. So the majority of work that we've done is objectives 4 to 5 and 6 to 7. Where we've been somewhat lacking is objectives 1 through 3, is in terms of informing management. Getting more targeted research that could potentially influence tactical fisheries management decisions. And the reason that's been happening is because most of the work that we've done has focused on long-term ocean change, so multi-decadal, 30, 40, 50 years out into the future, which really doesn't benefit these year-to-year and seasonal tactical fisheries management decisions. I think this figure here from a paper published in 2017 by Tomassi et al. Kind of really captures what I just said in that last slide. Essentially what this is showing is the temporal spatial scales that these both fisheries management events occur, but also in terms of global climate processes occur. And so what you can see is that if you look at the far right of this figure in the top, in terms of global warming and long-term fishery management plans, industry long-term resource capitalization, this is really, we've been focusing a lot of our work with these longer century scale, multi-decadal projections of species distribution change. But I think where we need to move forward is moving more toward the left of this, looking on the x-axis, moving toward more of the left side, the shorter timescales, seasonal, sub-seasonal, and yearly timescales, which we're talking about annual catch limits, monitoring enclosures, and industry operations. The problem, though, that we've been having is that the forecast skill for ocean conditions is very, very poor relative to other coastal regions around the world in the US Northeast. And if you remember back to that oceanography slide I showed you, it's a very complex system. And a lot of ocean models are challenged at forecasting conditions even just a few months out in terms of sea surface temperature, let alone more complex variables like bottom temperature. So what do we need? So what is needed to achieve climate-ready fisheries management and protective species management? So, essentially in terms of, 5 main things that are needed. There's a lot more than just these 5, but these are some of the more high priority things that I think we need. We need more studies that identify the mechanistic relationships between stock assessment variables such as recruitment, growth, natural mortality, and climate ocean variables. I think these are key. And when I talk about climate ocean variables, I'm not just talking about ocean temperature, also things like circulation, changes in ocean acidification, primary production, secondary production. Without these mechanistic studies, we really don't have much to go on when we're projecting long-term change or even forecasting near-term change. So we need to have these robust observations, but also these laboratory process studies and historical modeling studies that can get at these mechanistic underpinnings between the ocean change and living marine resources. And then following on that, we need more skillful ocean forecasts that operate in the time scale of fisheries and protected species management. Most of the work we've done, like I mentioned in the last slide, has focused on the long term, which may benefit things like management strategy evaluations, long-term fishery management plans, but these enhanced monthly, seasonal, annual forecasts might benefit these tactical management decisions. We also need a more unified NOAA ocean modeling system that produces high resolution, regional ocean hindcast forecasts and projections. I want to highlight the need for not just the high resolution, which I think was exemplified in that last animation I showed, but also the need for these more skillful hindcasts. We have our surveys that go out there, but obviously, especially with COVID last year, we've lost a lot of observations. And so we rely on these ocean historical hindcasts to fill in those gaps where our observations aren't covering things both spatially and temporally. And then to build off that, we need more skillful forecasts and long-term projections using these high-resolution models. And then for 4 and 5, communities of practice, linking the resource managers and scientists to communicate the best available climate science regarding climate fisheries and protected species issues. And this is really key. I think sometimes a lot of stuff gets lost in translation. So establishing these communities of practice will hopefully enhance the communication of this information. And then finally, we need these cross-NOAA regional teams. So multi-line office collaboration within NOAA to support the production and application of state-of-the-art ocean models and their simulations and information. So in 2019, I'm going to wrap up here soon. NOAA, OAR, and NIMS basically steered the formation of the NOAA Climate and Fisheries Initiative, which is currently just a white paper. The white paper was published last year, and the 4 major action items that came from this initiative were to enhance the utility of existing climate information that we already have, advance NOAA's regional modeling system, establish regional teams and communities of practice, and then fuel innovation and applications through targeted research, which, as you saw before, we've actually been doing quite a bit with a lot of these piecemeal projects and grants. So this circle diagram gives you somewhat of a sense of how the initiative could work. So essentially, building off of NOAA's state-of-the-art ocean modeling system, running up through the smaller circle, multi-NOAA line office, NOS, National Ocean Service, OAR, National Weather Service, and NIMS, and then these regional ocean runs. So you can have, for example, a ROMS-esque or a regional ocean simulation covering the entire US East Coast, shown here, followed by the outside circle, which would benefit from that entire East Coast run, being the Northeast Fisheries Science Center, the Southeast Fisheries Science Center, and folks in the Gulf of Mexico. Similarly, would be the same case with our folks out in the West Coast, having an Arctic model run, a West Coast model run, and Pacific Islands run. And then the outer edges of the circle, essentially the regions that can actually influence management, can feed back on the inner circles, basically giving feedback so that when they're designing the ocean models in NOAA, they're getting feedback what the regional needs are coming through multiple line office collaboration. So the idea of the CFI is to basically look at what is the potential in 2 years out and what is the potential in 5 years out. So the 2-year plan, which basically consists of some pilot studies which are going on right now, which I'll get into in my last slide, are essentially establishing communities of practice, linking resource managers, researchers, and forecasters to ensure they have the best available climate fisheries information for resource management. The second component of this are these new state-of-the-art MOM6 ocean modeling systems. So MOM6 is NOAA GFDL's state-of-the-art ocean model, which was used in the latest IPCC AR6 report and their submission in terms of their Earth system and global climate models. And so the idea is to have these new regional runs running at a high resolution to produce these pilot studies of regional climate ocean hindcast predictions and projections for coordinated assessment and evaluation. And I'll show a slide on that in just a bit. And then establish regional teams, which are helping to guide, test the regional model development and the research results. And then in terms of leveraging past and future investments to make data and information available for use, and then new investments driven by stakeholder needs for information applications. So getting feedback from councils on our SOE report and things that we can do in terms of producing more skillful ocean hindcasts and predictions. And then so in 5 years, the idea is to have these regional MOM6 ocean modeling systems in place and operational, essentially delivering next generation hindcasts, nowcasts, forecasts, and projections, ultimately for the use of living marine resource management. And what's really critical here are these cross-NOAA regional teams to support the production and application of these regional ocean model runs. And this is really key here. So essentially having the regions, give their feedback in terms of what they need in terms of council decisions, state ecosystem reporting, stock assessments, and what the ocean modelers can do to provide that information that's needed. What are the challenges that we're facing in terms of simulating the Northeast Shelf, and what can we do? What is needed by fisheries managers and scientists to basically get to climate-ready fisheries management? So going from the modeling side to the management side. And then I won't cover everything in this slide, but essentially, it's similar to the 2-year program, but what we'd like to have in 5 years is a solid permanent infrastructure within NOAA that's a multi-line office collaboration that essentially is serving the needs of the National Marine Fisheries Service to get us to climate-ready fisheries management. And essentially that is coming down to enhanced regional modeling that is giving us improved hindcast, forecast, and long-term projections at a high resolution. So this slide here is just giving you an example of what one of these Climate Fisheries Initiative pilot studies looks like. So this is a NOAA GFDL MOM6 regional run running surface chlorophyll in the ROMS domain, so covering the Gulf of Mexico, up through the Gulf of St. Lawrence and Scotian Shelf. And what this is showing you is high-res surface chlorophyll running in MOM6 with biogeochemistry. And so this is currently underway right now. Andrew Ross and Charlie Stock at GFDL are leading this research. And the idea is over the next year or two to have a brand new US East Coast high resolution hindcast, and eventually using the same model for sub-seasonal, seasonal forecasts and projections. And this is including both physics and biogeochemistry, not just physics. And so another pilot study that stemmed off the newly formed CFI is ENCLINE, so the Northeast Climate Integrated Modeling Project. This is similar to what the folks have done out in Alaska in the Bering Sea, so we kind of stole their acronym. But this project is currently using the upcoming research track assessments for Atlantic cod, Southern New England yellowtail flounder, and black sea bass. And it essentially is synthesizing, coordinating climate ocean models, ecosystem population models, and human dimension models for these upcoming research track assessments to hopefully inform those assessment groups once they're established, and they can actually use this information to potentially use ocean and climate information to potentially use operationally in the stock assessment moving forward. And this is my last slide here. In the meeting briefing materials, you should all have received a copy of our seminar series list. So this year we established a US Northeast Climate Fisheries Seminar Series. Each month, at the end of last Thursday of each month, we're hosting a different presenter and different talk. And all the talks are focused on US Northeast fisheries, climate protected species issues. In 2022, we may actually go to 2 talks per month. There's a lot of good work going on. And this is including both government, scientists, NGOs, and also our academic partners. And so this is the current seminar series schedule for this year. And on that PDF document that you should have in your brief materials, you can actually subscribe to individual talks if anybody's interested. And I'll stop there for any questions. Thank you very much.
Vincent, thank you so much for your presentation. A lot of really good information. I am certain that there are going to be some interest in asking some questions. There is no action required at this time, but I just want to thank you for your presentation. I see a few hands on my screen. I'm going to start with Peter Defer, and then Kate Wilkie, you're on deck. Go ahead, Peter.
Thank you, Mr. Chairman. I appreciate that. And thanks, Vincent, for a fabulous presentation, and one that, when I couple it with what we heard yesterday from our good friend Sarah, scares the bejesus out of me. So I think we need to recognize that we're going to have to be doing some things different. But I did have a couple of questions. They might be in some of the printed material you've got. One of them had to do with the criteria used in the assessing vulnerability of the port. So what are the characteristics of ports? And another one is related and unrelated. To what extent do land-based sources contribute to alteration of your measurements of ocean conditions? And then I have one more observation after that.
Okay, so your first question regarding the social vulnerability study, is that what you're referring to?
Yeah.
Okay, what were the details that you wanted? What was the details of your question regarding the social vulnerability?
So what are the characteristics of social vulnerability that go into determining that? Because, you know, what we've looked at in some of our assessments has to do with fisheries value, number of fisheries, et cetera.
Right. So what Lisa did in that study, Lisa Colburn et al., they were mostly looking at diversity and catch at the different ports. So yeah, so I don't know if I can go back to that slide. Let me see if I can go back here. Oh yeah, I can. Great. What they were doing. So the larger circles were essentially, you know, the ports that had higher landings. But basically, the ports that were in red were those that had a lower diversity of catch. Those that were in yellow and blue had a higher diversity of catch. So basically, saying that those ports that had a higher diversity of catch would be able to adapt to, you know, future ocean change just because they had a higher diversity index. So it was mostly focused on diversity. Does that answer your question?
Yes, that's perfect. Thank you very much.
Okay,
And I'll
sure.
go back and look at Lisa's publication. The second question was,
Okay.
to what extent are land-based sources a significant contribution to changing ocean water quality conditions?
So are you saying, so is the question land-based sources of things like nutrients, runoff, eutrophication?
Yeah.
Is it?
Yeah, and it could be direct land-based or, discharge into the bay, which then
Right.
contributes to, so.
Okay, yeah, it's a great question. So I mean, mostly what I showed today was focused on, not pelagic, but shelf waters that are,
Right.
in less contact with coastal sources. So now, of
Right.
course, a lot of the species, commercial NREC species and protected species, are using estuaries and rivers in the Northeast. So, I didn't get into that a lot today, but we have made progress on, for example, Andrew Ross at GFDL, in terms of looking at forecasts and projected change in estuaries. Now, in terms of the land sources, their influence, there's absolutely high level connections between things like surface runoff,
Right.
high precipitation events where we've seen changes in river flow, and of course eutrophication. Places like Long Island Sound, where there's lots of eutrophication, toxic phytoplankton, algal blooms, things like that. Hypoxia is an issue.
Yeah.
Changes in dissolved oxygen. So yeah, that's a whole, if I had 2 hours today, I would be able to go into a lot of our work looking at our watersheds, but that is definitely a large part of our work, which I wasn't able to cover today. But yeah, it's a huge issue. It's a huge issue. Absolutely.
Yeah. Okay. So yeah, and the third one was just an observation that by the time you reach the end of your presentation, it occurred to me that we also need a ton more monitoring of ambient conditions in a variety of places on the ocean. So thank you.
Yeah. Thank you very much.
Yeah, thanks, Peter. Thanks, Vincent, for your answers. And so, if there is additional information that you think would be helpful for the council, you just made the comment that if you had more time, you could have gone into. Maybe we can set something up for a future meeting to expand on what it is you already presented. So, I can work with Chris and you, and we can try to figure out how to get you back on the calendar.
Sure, absolutely, and I can send around, once the report is published. It should be published soon. I'll send our regional action plan synthesis report, which will highlight all of our work that we've done in the last 5 years, which I think might be useful.
Yeah, excellent. Thank you. So I see John Hare, your hand's up. Did you have something that you wanted to add to what was just discussed, or can I go to Kate?
Yeah, just if I may interject for a moment. Thank
Please,
you very much,
go ahead.
Mr. Chair.
Thanks, John.
As questions and sort of directions for us come up during this presentation, I just remind people, Dr. Dubois gave a presentation, a conversation inviting input in terms of what the agency should be doing with regards to climate change. And, Peter, your comment about increasing observations and increasing the connection between what's going on the land and what's going on in the ocean, and a better understanding of community vulnerability. I think all of those questions would also be suitable to send to the agency as part of, Paul's call for council response or individual council members response. So just, you're going through this and asking questions, turning your questions into a response to the agency through the executive order call is another way to help us be able to take this information into account.
All right, excellent, John. I appreciate that. Thank you very much. Kate Wilkie, I had your hand up. Did you have anything you wanted to add, or I saw it go down? Did you have a question?
I do have a question.
Yeah, go for it. Go ahead.
Having technical issues. Peter was just starting to touch on my question, but thank you, Vincent, for the really very cool presentation with so much information and borderline speaking another language at times. So I'm maybe you can kind of clarify for me. At the very end, you showed 2 slides where that listed several bullets about where you guys are going in the next 2 years and then in the next 5 years. And I was just wondering what's required to make these advances in modeling. Do you basically need more sensors in the water to collect more fine-scale data? And if so, is there a plan to do that? And I assume it requires more dedicated funding.
Yeah, great question. So the last thing you said is 100% true, dedicated funding. You know, one thing I didn't mention with these high resolution model runs, which as you can see are so critical for coastal fisheries and management decisions, is that they're costly. So, you know, running global models at a low resolution is a lot cheaper than running a global model at a high resolution. It's more computing time, more power. It's just larger investment. So not just that, but also having the infrastructure, the personnel that are dedicated to not just the model development regionally that can benefit NIMS, the National Marine Fisheries Service, but also the feedback between the Weather Service, Ocean Service. So it's not just NIMS and OAR, it's our other line offices as well. And so having dedicated full-time personnel that can, you know, that is their 100% full-time job, that's their day job, to do just that is really the core of it. And so we're hoping in the next few years that we'll see, you know, a change and that we'll be able to actually have a permanent infrastructure. But yeah, you're absolutely right. There is a cost at running these high resolution simulations from a technical standpoint, but also just having the personnel infrastructure there so that the information can be communicated and ultimately inform management decisions.
Thanks. That's helpful to understand. And when you say running a global model is expensive, so to me it sounds like the data is available, but it's just actually having the personnel and the time and dedicated people to do it.
Yeah. So the ocean models, they're not always using observed ocean data. So the observed ocean data, we always need more ocean observed data so that we can validate the models, right? So these global and regional models are essentially trying to simulate the real world, right? So we need to have better observations, which of course also requires additional funding, so that we can have, you know, higher resolution time series of observations to compare to higher resolution models. So for example, I mentioned ocean pH. We don't have a lot of ocean acidification measurements. So when we have models that are simulating ocean pH throughout the water column, how do we compare those models to observations if we don't have, you know, bottom pH measurements in the Northeast Shelf? So that's where that data becomes critical so that we can validate our models, which gives us more certainty moving forward. If we know the model performs better in the historical time period, that gives us more uncertainty with our predictions and our projections.
Thank you.
Okay, thanks for that. John Hare, your hand's still up. Did you have something you wanted to follow up with?
No, sir. Thank you. I'll take my hand down.
Okay, thank you. Jeff, I'll get a chance to come to you in a minute, but I'm going to stick with the council at this point. Next, I have on my list Tony DeLernia. Go ahead, Tony.
Thank you, Mr. Chairman. Dr. Saab, I'd like to add my voice to the chorus that's been congratulating you and thanking you for such a wonderful presentation. As a former instructor of oceanography, I enjoyed it very much. I have two quick questions I think you might be able to answer. One of them was that you said that you knew or you had a list of covariants for summer flounder and black sea bass. Could you just briefly tell me what you think those covariants were, or what you have currently in your system here? How do you look at those covariants?
Yeah, so I don't have the figure for summer flounder. This is the figure for black sea bass. I think I'm still sharing my screen if you could see that. So what we found for black sea bass in particular in this study, we looked at bottom temperature, surface temperature, depth, sea surface height, bottom salinity, surface salinity, and rugosity. We found that bottom temperature was the primary variable impacting black sea bass habitat. And this was based both on the fall, spring surveys, but also fisheries dependent observer data throughout the year. So bottom temperature was the #1 variable, and that was followed actually by sea surface height, which was surprising. So even though we didn't know, you know, the mechanistic link between changes in sea surface height and black sea bass habitat, it still showed up as one of the higher order variables impacting habitat. Summer flounder, I don't have that figure. I believe bottom temperature was also, but I also think salinity was also a factor in the summer flounder habitat model. I'll have to go back and check the paper.
Now, is this the same diagram I was looking at when you were talking about projections on species distribution going forward?
Correct. So what this is showing, what this figure shows is a projection of black sea bass habitat. On the left panel is when you look at all the variables.
That's right. Okay.
Right, and the right panel is just looking at temperature. So the temperature only projection of black sea bass looks very different than the full model, which uses salinity and surface height as well.
Very good. Thank you very much. No more questions. Thank you.
Sure, you're welcome. Thank you.
All right, thanks, Tony. Adam Nowalski, you're next. Go ahead, Adam.
Good morning. Thanks very much for
Good morning.
recognizing me. Thanks very much for the presentation. Will probably come as no surprise to a number of council members that have heard me bring this paper up before. You had referenced a number of pieces of literature in the presentation. One paper I did not see explicitly referenced here is the Taylor-Bigelow Graham paper from Fishery Bulletin 115, 1957, from the Fish and Wildlife Service. Said on the cover it was for sale for 40 cents. I suspect today we'd probably pay a lot more money for this type of information, but it must have been a great deal back then. I bring the paper up because I'd like to know what your consideration has been as you've done this work with the findings detailed in that paper, the correlations in the 30-year period prior to the publication of this paper. I find very striking to things we're seeing today. Declines in American lobster in the mid-Atlantic, increases in abundance in the Gulf of Maine, menhaden that had not been commercially exploited since the end of the 19th century, reappearing in the late 1940s and becoming commercially exploited. The magical appearance of a species of fish that no one could identify in 1950 off the coast of Maine that turned out to be a black sea bass. The increase in temperatures within the Gulf of Maine in the 30-year period from 1920 to 1950. Again, understanding that past performance isn't always indicative of future results. There are a ton of parallels here. I brought this paper up before and was wondering what your thoughts were on the applicability of it and the comparison to what we're seeing today.
Yeah, thank you for bringing that paper up. I know it's an old paper, but it's got a lot of anecdotal data, but it's a key paper. So in that paper, we are seeing, like you mentioned, we're seeing parallel responses in our species observations. So for example, you mentioned black sea bass. In that paper, they did report. So that paper was essentially looking at that there was a period of warming in the U.S. Northeast in I believe it was the late 1940s, early 1950s. There's various theories as to why the ocean was warm. Part of it's related to the Atlantic multi-decadal oscillation, the AMO, and the position of the Gulf Stream. So what they showed in that paper were similar things that we're not just projecting forward with climate change, but also what we're seeing in our surveys today. Black sea bass in the Gulf of Maine. They also reported more white sharks closer to Cape Cod. We're certainly seeing more white sharks off Chatham over the last 5 to 6 years. Not just we think due to changes in temperature, but also due to changes in their favorite seals to eat. So I think the similarities are key. And I think the main difference though between what that paper observed and what we're seeing today, if you look at the temperature trends back in the 1940s, 1950s, the difference between then and today is that the wintertime ocean temperatures were warming substantially in the 1940s and 1950s. Today, in our current data sets, we're not, that one figure that I showed and that Sarah showed yesterday in the SOE, our wintertime sea surface temperatures and bottom temperatures really haven't changed that much. There's no significant change in wintertime temperature. So I think it's going to be interesting to see some of the differences. So the parallels, of course, are interesting, but the differences because our winter temperatures really haven't changed that much. We're seeing most of the warming occurring in the summer and fall, as opposed to what they observed in the 1940s and 50s, which were both the winter temperatures and the summer temperatures were warming at a pretty comparable rate. But you're absolutely right. Those anecdotal reports in that classic paper really does show similar things that we're seeing in our survey data today and what we're projecting forward.
Okay, thanks for that. Michelle Duvall, you're next. Go ahead, Michelle.
Thanks, Mr. Chairman. And thank you, Vincent, for the amazing presentation. I'll just add all of my accolades to those that have gone before. I wanted to just follow up really quickly on a point that both Peter and Kate touched on, and that was about the need for additional observations really to just improve the performance of the models. And, you know, would you say, I guess it's a two-part question. So is there a need for more observations in the coastal shelf portion of, ocean geography, or more open ocean observations? And I guess the second part of that question is, I'm just thinking about collaborative approaches to obtaining those observations. I mean, obviously, I've seen some of the collaborative approaches that are used in the Gulf of Maine with, temperature sensors on lobster traps and things like that. But just wondering about, larger community of practice type of approaches to obtaining observations with, sensors on, like with the ocean shipping industry, for example, and stuff like that. And, I assume that, you have worked and reached out to the cooperative research branch, and thinking about creative ways to try to, obtain the observations that you need, in a really efficient way that also, brings stakeholders into the process. So
Yeah.
Thanks.
Yeah, no, great question. So I think, in terms of temperature, we do have a lot of temperature. You can never have enough temperature data, right? So surface measurements for temperature, I'm just giving an example here, are pretty good. We have satellites for that. So when our ships are not out there, when there's a global pandemic and we can't measure, at least we have our satellites measuring surface conditions. The problem that we have in terms of temperature are the mid-water and bottom measurements. So those, of course, are more far and few. We don't have the measurements daily like we do for surface temperature. So we do rely on, obviously, cooperative research is huge to fill in those gaps. Additional surveys outside of the Northeast Fisheries Science Center, glider data, Nearcoos and Maracus data coming from fixed ocean stations, and of course I just mentioned the gliders. So I would say you can never have enough observations. So in terms of physics, we have a lot of temperature data in the surface. Now, in terms of the biology, that's where I think we're lacking. We don't have, we know that temperature is important, for example, changing fish distributions, but as you can see in this slide here, temperature is not the only factor. So we need to have more biogeochemical observations, actually. So I would love to see, more phytoplankton, zooplankton observations, which then can inform our biogeochemical models, which are coupled to these physical models, so that we can have a better sense of how living marine resources are responding to not just temperature, but also things like changing ocean pH. You have to have a biogeochemical model to resolve ocean acidification. How are fish responding to, and larval fish responding to changing zooplankton size classes? For example, we know that right whales, have been in trouble for quite a while now. And there's theories out there that their prey, Calanus finmarchicus, which is a lipid-rich fatty zooplankton, has been changing. We don't have a lot of in situ data of cowfin to confirm a lot of those theories. So we need these observations of biogeochemical processes. They're just as important as the physical processes, I think, and that we can have better biogeochemical simulations, which can then also benefit our models.
Okay, thanks for that. Thanks for that question, Michelle. Thanks for your answer, Vincent. Chris Moore, I have you, and then I'm going to go to the public to see if anybody from the audience has any questions or comments they'd like to ask. So go ahead, Chris.
Thank you, Mr. Chairman. Hi, Vince. I agree with Kate. There's a lot of cool science here, and certainly appreciate the presentation today. I have a quick question for you. You mentioned, during your presentation, you highlighted the operational aspects of all this, and certainly, that's something I'm very interested in terms of informing management. But you mentioned an initiative and I can't remember how it linked to councils or what that specific initiative was. Oh yeah, that one.
Right. Yeah, this one here. So this is the NOAA Climate Fisheries Initiative. It's brand hot off the presses. Not many folks know about this. So it's essentially an initiative. It's a white paper that was co-steered by NOAA, OAR, and National Marine Fisheries Service, and there was also incorporation of the Weather Service and NOS. And essentially, the idea behind this initiative is to, and then these are the 4 actions listed here to the right. I was a co-author on. There was originally 2 working groups. One working group was focused on long-term climate change projections, and the other working group was focused on the near term, the forecasts. And the 2 documents actually ended up very different, and then they were combined into a single initiative paper, which is the cover shown here. I don't know if it's available to the public yet. I can check with John Hare on that. He's on the steering committee, and we can figure out if we can get the document out to folks. I know it wasn't in the briefing materials, but this is essentially, where we want to go moving forward. And someone mentioned earlier that, obviously funding is a key component of this. But in order to have, this is, I don't want to say it's all modeling exclusive. It doesn't really talk a lot about our need for, we do need improved observations and mechanistic studies. But really, the Climate Fisheries Initiative is mostly focused on modeling, improved regional modeling, high resolution, hindcast, nowcast, forecast projections that can ultimately inform practical fisheries and protected species management decisions. And the framework involved is kind of, in a general sense shown in the circle diagram, where, the ocean models, state-of-the-art ocean models are being designed by places like GFDL, working closely with line offices like Weather Service, OAR, NOS, and NIMS, and then having these regional runs, so an East Coast run, Arctic, West Coast, Pacific Islands. And then on the outside bands of the circle are really where the stakeholders, the fishery scientists, the councils come into play. And then those outer circles can feed back on the inner circles, which basically can go back and forth between the ocean models at the core, going back to the outer circles, influencing the targeted research that's needed that can actually influence fisheries management decisions. So that's the idea behind the CFI, if that helps.
Yeah, thank you. Yeah, I'm very interested in seeing a copy of this. And just quickly, so this focuses a lot on, obviously, on the science and modeling.
Right.
What part, or is there going to be another document, do you think, that's going to talk about how it's going to influence or inform management decisions, or is that part of this document as well?
So I think that's going to come in with the 3rd action plan here, establishing regional teams and communities of practice. And so, so I think each region has its own specific needs. The Northeast is going to have very different, dealing with 2 management councils and a state commission will have very different needs than, say, folks working in the Bering Sea. So it'll be very region specific in terms of these communities of practice that are established. So I think that's where the CFI would help get that information translated into management, would be, in terms of getting enhanced regional level communities of practice.
Excellent. Great. Thank you.
Thanks, Chris, for those questions. Let me look and see at my list here. John, did you have something? John Hare, did you have something you wanted to add?
Yeah, thank you very much, Mr. Chair. And yeah, thank you for the question, Chris. And, this, 3 sort of established regional teams and community of practice, and then 4 fuel innovation and application. So this initiative calls on each region to identify some early applications for this information. And certainly if this initiative is funded, and if we're able to go forward with it, we'll be coming back and sort of having conversations probably at the NRCC about what should we choose as our sort of targeted applications. Vince had mentioned the ENCLINE project, which sort of borrows a lot of this sort of thoughts from what's going on in Alaska. One of their example species is black sea bass. And so we're trying to sort of develop some capacity around black sea bass. And the other application, sort of near-term application from a science center perspective, I think is the scenario planning effort, which is starting now. We heard the talk from Emily earlier on that. And so we sort of see in the Mid-Atlantic Council, realm, trying to use this initiative as it is developing in sort of those two applications. But we'll, if this is funded, if we are able to move forward with this, we'll certainly be talking with the council about additional applications or what support for those two applications would look like.
All right, thanks for that information, John. We're pushing up on our time limitations here, but I do have two members of the audience from the public for questions or comments. I'm going to go to Bonnie Brady and then Jeff Kalin, and then we'll move on. So go ahead, Bonnie, you're up.
Hi, thanks, Mike. Can you hear me okay?
Yep, you're good.
Hi, Bonnie Brady, Long Island Commercial Fishing Association, and Vince, thank you very much. I was wondering, first of all, there's a map that you had about climate vulnerabilities in various fishing ports. I'm wondering if you could quickly give me when you mean for mixed, and is that based on dollar value of the port or regarding the vulnerability?
I believe it was, yeah, I believe it was, I have to double check with, I wasn't a co-author of this paper, but I believe it was both the value and also the diversity of the ports, correct?
Okay, so maybe if you could throw me that paper, or if I didn't see anywhere on the Mid-Atlantic webpage, if there was a listing for that, that would be interesting. A couple of quick questions. A lot of your modeling involves what I heard you say is the OOS systems. Have you guys looked into, obviously, I think you're aware, the high frequency radar, the CODAR systems that measure ocean currents are going to get knocked out by radar, as the National Ocean Service mentioned back in 2014 when they were talking about the Equinor project. So have you all thought about some sort of fail-safe if those systems go out regarding your modeling? And also, what about long-term projections of wind blockage effects? And I've seen a couple of geophysical papers done. I'm not sure if Rutgers is doing something or not about the possibility of losing ocean breezes, which determine upwelling, downwelling. I heard you mention phytoplankton and right whales. Is there anything in your mix about any of that? Thank you.
Yeah, sure. So I'll try to address the first part of your question in terms of what our plan is for when some of these these critical observation systems, if they get defunded or get knocked down, like you had mentioned, the Rutgers CODAR work, and that's highly regional, and we have used some of those surface velocity measurements for some of our work. But what I mentioned earlier in terms of the need for more observations is just so critical. However, when we have situations where funding is limiting observations or personnel or whatever the case may be, this is where the NOAA Climate Fisheries Initiative, I think, can come in, because I know we talk about improved forecasts and long-term projections, but a large part of this initiative is also improved hindcasts. And so if we can get better models, regional high-res models that are simulating all sorts of ocean variables. So for example, with the CODAR measurements, surface velocity, the models would be simulating surface velocity. So if we have model, nowcasts or, weekly forecasts or historical observations that can, I don't want to say replace, but we could at least go to those model simulations when we don't have the in situ observations would be critical. And I think, really any near-term forecasts or projections in terms of how species could react really must benefit first from those hindcasts, those historical simulations in the region. So I hope that answers your question, but I mean, I'm less involved with the CODAR project than others, but those projects, whether it be Maracus or Nearacus and the glider deployments, those are absolutely critical to inform our ocean models, because we need those three-dimensional ocean properties to validate the models 100%.
Okay, and just a quick follow-up regarding cooperative research. I think the Flounders used to have some bottom sensor data, but is there any type of work that's in the hopper there regarding working with fishermen also for their historical data? Because somewhere either in their heads or in their documents, they've got a lot of that specific historical data that you're talking about. Thank you.
Yeah, thank you. Yeah, and we do, our cooperative research program does keep tabs and data archives from those vessels that are in fact providing physical ocean data. and it absolutely fills in the gaps that we're missing with our surveys, which are obviously limited both spatially and temporally. And of course, those folks are out there where they're actually catching fish and targeting areas where they're also observing ocean change. So yeah, we definitely use that data, and it's absolutely critical.
Thank you.
All right, thanks for that. Jeff Kalin, you're up next, and then we're gonna wrap things up. Go ahead, Jeff.
Yeah, thank you, Mr. Chairman, and members of the council. Jeff Kalin with Lund's Fisheries. I appreciate the time, but could you go back to slide 9, please, Vince? And I just wanted to say it's a very interesting application of the data and opportunity to look at it. I really take to heart Mr. Nowalski's question about the gram work that up in the Gulf of Maine, and that maybe things don't really change so much after all. Now on this one here, I'm looking at from 1970 to 2020. We have a center of biomass shift of all species of 1/2 of 1 degree of latitude, essentially. And that's 30 miles. And I believe from Hatteras to Montauk, it's 5 degrees, which is 300 miles. So this doesn't tell me very much, honestly. Certainly doesn't give me any need to be concerned based on, what we've seen over that period of time. Started in the fisheries in 1972, personally, relative to a diversity of catch and so forth. So, John mentioned the executive order comment period. So we were on the 23rd of March, and I think the need to be continue to be deliberative and gather data and everything is very important. The thing that I'm questioning is the crisis part of this whole thing. And I think if you look at the slide and pull out your navigation books, you'll realize that that's really doesn't tell us very much at all. And one of the things I'm concerned about in this presentation and just generally too is that we're not hearing much about emerging species. It's all bad news. I'll give you one example: chub mackerel. We've talked about it for years. Another one, is thread herring. Both the recreational and commercial fisheries have run into more of both of those species during this period of time. And it is true the herring may have left the building, and it probably is the change of the Calanus moving to the east, as you mentioned, Vince, which has also affected the whale activity down to the eastward. So I just wanted to point this chart out to the council and say that I don't see anyway a foundation for a crisis. So I hope the council continues to be deliberative and the Science Center continues to produce the data so we can manage the fish. And like Bonnie mentioned, I think we need to be doing some planning about what we're going to do for the loss of survey access with the 2,000 windmills that are being projected to be built between Cape Cod and Virginia Beach as a crisis, rather than a shift in species availability and negative impacts on communities. So I was going to mention slide 15. I wanted to ask the same question: is it value? You said it's both. So I guess I would like to see that, because again, we've seen a lot of squid. Maybe those red dots are based on scallop shifts, possibly. I don't know. I guess that's a question for you. I've said a lot here, Vincent, and
Yeah, that's okay.
I don't mean to come down hard on this, but yeah. So, like Bonnie said, if we could see that document, that'd be great. And thanks for the council. Appreciate it.
And I'll just touch real quickly. I know we're almost out of time. So your question about this particular figure, you need to keep in mind, this is an average of all species. Okay. So you're right that in terms of the actual shift of the center of biomass of all species, but you're talking about a survey sampling everything. So if you just took individual species from this, you would not see the smaller shift for some of these species that have moved north. So for example, if you just took American lobster out of here, or black sea bass or summer flounder, the distance moved north would be much, much more dramatic. So please keep that in mind when you're looking at this figure. I didn't use the word crisis at all in this talk, which I think is fine, but I think that the take-home message here is not that there's a crisis, but just that things are moving, things are changing at a very rapid pace. And I think someone mentioned that paper from the 1950s, the Taylor paper. That could give us a good sense of what's to come or what's happened in the past. So it's more of just, do we have the infrastructure in place to adapt to change on a seasonal or to yearly basis? Because we can see things are changing. And if we just look at the Northeast relative to areas around the globe, the U.S. Northeast has warmed much, much faster than other coastal regions around the globe. So we're in a region that is dynamically changing at an unprecedented rate. And so we're going to need to respond to that change, whether it's a crisis or not. But you also made a good point about new species moving in. And I think that's something we've talked about before, which I didn't have a chance to highlight, where climate change winners, climate change losers, new species moving in, things like, blue line tilefish, great triggerfish, things like things coming north of Hatteras, and other species moving out. And I think the question might be, are those species catchable? Are they as valuable? But yeah, good point on this figure, but I just want to make sure it's known that this is an average of all species.
No, that's great. And I don't mean to come down hard on you. And I didn't say that you said it was a crisis. That refers to the executive order call on March 23rd. So
right.
Anyway, thanks very much. Good work.
Thank you for your question.
Thank you, everyone. Vincent, thank you very much for your incredibly informative presentation. And I guess we can all look forward to continued discussions on this issue, given the climate and change in the ocean conditions interest of fisheries managers. So I want to thank you for your time this morning. I am going to move on, but again, Vincent, thank you so much for spending the time early this morning to present your information. I appreciate it very much. And I know that
you very
all
much.
the other council members, of course, appreciate it as well.
Thank you very much, Mr. Chairman. And I'll try to get that report out to you as soon as I can.
Yeah, if you can send it to Chris Moore, then Chris can just distribute it to all of us. That would be
okay. We'll
do.
Go.
Yeah, I appreciate
no problem.
That.
Thanks for having me, folks. Will do. I appreciate it.
Thank you very much. Take care. All right.